Okay, so today we're going to be looking at identity verifications. And what it means to verify an identity is we're going to be going back into the idea of geometry, where we're going to be doing a proof. We're going to be proving that the left side does in fact equal the right side. Now, there are two different ways that when we come to trig that you're going to run into with your teachers or your professors. Some teachers and professors like work to be only done on one side of the equation so that I can rewrite the left side so that it equals what is shown on the right, where after several steps I'll see that 1 does in fact equal 1. The other method is to work this as you would work an equation and work both sides of the equation until you get something equals itself. Now, both of these are justified in how you approach it. The idea is the fact that the left does in fact equal the right, and the best way that we can show that is by playing with both sides of the equation. The first way, where we only work one side, that is going to teach a little more vision and a little more ability to play with the expressions, because you were really having to dig in and get to the other side. The only downside to that is that if you don't happen to see the vision of how to get it to 1, you're stuck with only playing with one side. So what I would recommend you do is play with both sides of the equation until you get an expression equals itself. And if you do have a professor that likes you to only work with one, take the series of steps that led you there, and take the series of steps that led you there, and pivot and copy them down in reverse after you've found the equal. And that way it's just one continuous series of steps. You've done the same thing, but it's in a format that they best see fit. Again, it's just personal preference at this point. So let's go ahead and without further ado, let's jump into the first question and see, okay, I need to be able to prove that sine squared of theta plus cosine squared of theta over cosine squared of theta secant squared of theta is equal to 1. Now, we've done some lighter expressions like this, and the first thing that I would always recommend is that out of all the formulas, we have enough to memorize. Why don't we just go ahead and convert everything that's not a sine or a cosine into a sine or cosine? That allows us to focus on the manipulation of the numbers as opposed to just memorizing a series of formula. So I'm going to go ahead and say, okay, I have the sine squared of theta plus the cosine squared of theta all over the cosine squared of theta, and that secant ends up being 1 over the cosine squared of theta equals 1. And we see that just simply by rewriting the expression, it already lent us to something where we're going to have part of the expression cancel out. Cosine squared over cosine squared cancels out. I'm left with nothing in the denominator. So my next line is going to be sine squared of theta plus cosine squared of theta is equal to 1. Now, with this, I'm going to have to use one of the Pythagorean identities, which you may be familiar with, that says that the sine squared of x plus the cosine squared of x is equal to 1. I'm going to use exactly that to rewrite the left-hand side of my expression. I'm going to take my sine squared plus cosine squared and rewrite it as a 1. So I'm going to take this, and I'm going to rewrite that as a 1. So 1 equals 1. I have successfully proven that this expression is equal to the right-hand side. And at the end of that, I'm going to put QED. Now, QED stands for Quod erat demonstrandum. And quod erat demonstrandum is Latin for that which has been demonstrated, saying I have successfully demonstrated that yes, left does equal right, this expression does equal 1, because after working both of them, I got 1 equals 1. Done. So let's pop off into the next problem. Now this one, right off the bat, we see that there's a couple ways I could work this, but the first one that I'm probably going to do is rewrite this cosecant squared as something as a sine or cosine. So I'm going to rewrite that as a 1 over the sine squared of beta. Everything else I'm just going to go ahead and copy down. 1 over 1 minus the cosine of beta plus 1 over 1 plus the cosine of beta. Okay. Now with this, it brings us to our next point, our next helpful trick for solving these things. Our first step is always to rewrite anything that is not a sine or a cosine into sines and cosines. The other trick that is going to get you out of a lot of holes is if I can combine fractions in any way, shape, or form so that I'm dealing with one term and one term. That's going to help us get rid of a lot of unnecessary fluff. So because I have two different fractions, what I'm going to do is I'm going to combine them, which means that this right expression, I need to get a common denominator. So I'm going to multiply top and bottom by 1 minus the cosine of beta over 1 minus the cosine of beta. That way I haven't changed this expression. I'm going to do the same over here with 1 plus the cosine of beta. So 1 plus the cosine of beta times 1 plus the cosine of beta. Okay? Now what that will help me do, I'm going to go ahead and move that 2 up to the top. I'm going to distribute this 1, so I get 1 plus the cosine of beta, plus I'm going to distribute this 1, so 1 minus the cosine of beta. And then I'm going to go ahead and I'm going to FOIL this term because this is now my new denominator. So first times first, 1 times 1 gives me a 1. Outside, 1 times negative cosine is negative cosine of beta. Inner, so 1 times the cosine of beta is going to be plus the cosine of beta. And then last, so cosine of beta times negative cosine of beta is negative cosine squared of beta. Boom. So FOIL, first, outer, inner, last. We've got that set up. Now the next thing is we're going to try and combine and condense as much as we can. Now that this is one big fraction, let's get rid of what we need to. There's nothing to distribute here, so I can kind of ignore these parentheses. I'm going to say plus cosine of beta minus cosine of beta. Those might as well not exist. And I see the same thing in the denominator. Minus cosine of beta plus cosine of beta. They might as well not exist. So 2 over the sine squared of beta equals 1 plus 1 is 2 over 1 minus cosine squared of beta. We can see my expression is almost fully solved at this point. The only thing is I somehow need to relate 1 in cosine squared of beta to sine, because the top is good, I need to relate the bottoms. So that's going to bring us back to that handy-dandy Pythagorean theorem. So sine squared of x plus cosine squared of x is equal to 1. I have a 1 and a cosine squared, I have a 1 and a cosine squared. If I can get them both on the same side, maybe I could convert that into a sine. Let's go ahead and move that over there. Boom. So I have exactly what I'm looking at. So what I'm going to do is I'm going to rewrite 1 minus the cosine of beta as the sine squared of beta. Let's go ahead and rewrite that as the sine squared of beta. And I'm going to copy down everything else. And what I see is that I have an expression that is equal to itself. Quadrate, demonstratum. I have successfully proven that 2 cosecant squared of beta is equivalent to 1 over 1 minus cosine of beta plus 1 over 1 plus cosine of beta. I can now use that identity wherever I might need it anytime in the future. So what I want you to try out is I want you to try out the next one. Go ahead and pause the video, unpause it when you're done, and see all you did. Perfect. So if you follow the 2 guidelines, the first thing is always going to be rewrite what is not a sine or a cosine as a sine or a cosine. So 1 over cosine squared of alpha. Minus 1, sine squared of alpha minus 1 equals negative sine squared of alpha. So we get that. The next thing is we're going to try and combine any fractions. So I see that I have a fraction right here. So I'm going to try and get that taken care of. So I'm going to go ahead and multiply top and bottom by the cosine squared of alpha. So I have 1 minus cosine squared of alpha. So they're both over the cosine squared of alpha. The other thing I might notice is that this is my Pythagorean theorem again. I could go ahead and I could rewrite that using that sine squared of x plus cosine squared of x equals 1. I notice that if I have sine squared of x minus 1 is negative cosine squared of x. I could rewrite what's inside the parentheses as opposed to two terms as a single term. So I'm going to go ahead and do that as well. I'm going to make that a negative cosine squared of alpha. Boom. So I have this. I also notice that now that I've rewritten that, this cosine squared over cosine squared cancels out, and I'm left with 1 minus the cosine squared of alpha times that negative sign, so times negative 1 equals negative sine squared of alpha. Again, I see another Pythagorean identity. If I take that cosine and move it over, I will get 1 minus the cosine. So I know that that will be rewritten as the sine squared of alpha times negative 1 is negative sine squared of alpha. If I distribute that negative sine squared of alpha equals negative sine squared of alpha. That's enough to say quadrate, demonstrate them. Boom. And so that's going to bring us to a few more that we can look at. Why don't you go ahead and pause the video, try this one. It should be no more than about 2 steps. Now, there's several paths that you can take with these, but most of them, if you follow that standard set of guidelines, are going to knock out most of the steps within, I'd say, a relatively reasonable scenario, probably 4 or 5 steps. So go ahead and pause the video, try number 7, try the 2 steps of rewriting them as sines and cosines, and then combining any fractions that you can. Okay, now that you've had a shot, you'll notice that I can rewrite all 3 of these. The tangent is the sine over the cosine, cosecant is 1 over the sine, and secant is 1 over the cosine. We notice that next the sine over the sine is going to cancel out. So we're left with 1 over cosine equals 1 over cosine. Quadrate, demonstrate them. Done. Again, go ahead and pause the video, try this one out. Okay, now that you've had a shot, this one, I see I have the cosecant and the cotangent both of gamma, so I'm going to rewrite this as 1 over the sine of gamma. I'm going to write this as the cosine of gamma over the sine of gamma. So I get that. The other thing that I notice is the fact that I have 2 different fractions. They're both over the sine of gamma, so I'm going to go ahead and combine them. So 1 plus the cosine of gamma over the sine of gamma. Okay. So the other thing that we see is we notice that these are almost the same thing diagonally speaking. I have a sine and a sine. I have a 1 plus and a 1 minus. At some points, you can even treat the proof, especially if you're working with both sides, almost as though you're working an equation, which means that if I multiply both sides by the sine squared of gamma, it's going to cancel out over here. So I'm going to say, debating on if I have enough room to do this, cancels out. But if I multiply the left, I'll also multiply the right. Doesn't cancel out over here. But now that I've done that, I can also multiply both sides by 1 minus the cosine of gamma. So 1 minus the cosine of gamma, 1 minus the cosine of gamma. And then these cancel out. Not over here, but what I've done is I've brought them all to the same level. I no longer have a fraction. I have 1 minus the cosine of gamma, 1 plus the cosine of gamma, equals the sine squared of gamma. At this point, I'm going to go ahead and I'm going to FOIL this. First, outer, inner, last. 1 plus the cosine of gamma minus the cosine of gamma minus the cosine squared of gamma. cancel out what I can. Those go away. And I'm left with 1 minus the cosine squared of gamma, which hopefully at this point you recognize this is the Pythagorean identity that I can rewrite as the sine squared of gamma. QED, quaderat demonstratum. Done. And now this one specifically, you could have worked many, many, many different ways. But again, we're taking simply one approach to get from the top to the bottom. What you might have done is you might have gone ahead and tried to rework the right-hand side of the equation to get cosecants and cotangents. There's really no limit to how you get to the answer. In fact, if you're working a particularly hard problem and you seem to be making it more and more complex, one of the easiest pieces of advice that I can offer is go ahead, take a pause, work on a different question. When you finally come to that answer, come back to this and start over fresh. What you might have done is you might have changed part of the expression that is going to make your life a little more difficult. Not that you can't get there, but that the relationships are harder to see. And by taking a different approach with a fresh mindset, it allows you to quickly and efficiently get to where you're supposed to be going. So that being said, there's several ways that we could work this. This is a fraction, so I could go ahead and treat it like an equation and go ahead and put everything all in one line. Or I could go ahead and rewrite everything as a sine or a cosine and work it that way. So what I want you to do is I want you to pick whichever way you think is the best fit and give that a shot. Okay, so one of the things that I'm going to do is I'm going to go ahead and I'm going to rewrite everything as a sine or a cosine, which, as you'll realize, that's going to make this take a few more steps than if I'd worked it like I'd worked an equation. But again, it's just a consistent approach that I like to take. So cotangent is cosine over sine. Because it's squared, that is also squared. All over 1 plus, this rewritten is going to be 1 over sine of theta. Equals 1 minus the sine of theta over the sine of theta. At this point, I'm looking at trying to combine this lower fraction so that I can combine top and bottom. But first, I need to multiply by sine over sine. That'll leave me with a cosine over a sine. And then on bottom, now that I've combined this, sine over sine gives me sine plus 1 all over sine. Perfect. Next up, I'm going to change flip. So I get cosine squared over sine squared times sine over sine theta plus 1. I notice that I have a sine and a sine, which are going to cancel out, not the whole bottom, but part of the bottom. And I'm left with a sine of theta plus 1. I'm left with a sine all on the bottom. Okay. The next thing that I want to do, just simply to make sure that this is in the same expression as this, is I might want to multiply times a sine of theta plus 1 on this side, because I've got part of the denominator. I want the other part. Now, it's not with the intentions to add, but if I just multiply by the sine of theta plus 1, what I'll have is I'll have identical denominators, and then after this point, I'll be able to simply look at and work with the numerators. Let's go ahead and draw ourselves a dotted line. And that's going to leave me with the cosine squared of theta over sine of theta plus 1 equals, I can FOIL this. So first times first is sine of theta minus 1 minus sine squared of theta plus sine of theta all over sine of theta plus 1. And now that I see the fact that I have identical denominators, I can quite literally cancel them both out by theoretically multiplying both of these sides by sine of theta times the sine of theta plus 1. That would cancel out here and here. I'm just looking at the top. In addition to looking at the top, I see sine of theta minus sine of theta. Yeah, that is supposed to be a minus sign. So I have cosine squared of theta equals, let's see. So that would be a sine of theta plus 1. 1 minus sine squared of theta. At this point, we recognize this is a Pythagorean identity that I can rewrite as the cosine squared of theta equals the cosine squared of theta. QED. I'd error it, demonstrate them. Now again, if I had simply worked this as an equation from step 1 by multiplying that up here and this over there, what we'll see is that the sines and the sines over here will cancel out a little faster, and then we'll end up again canceling out some sines in this process. You might shave a few steps off, but in the end, this process did eventually get us to the final answer. And so that brings us to our final question. Here we have tangents. So again, keep in mind that the way of rewriting sines and cosines is in fact a guideline. There may be a way to slightly work this faster if you notice something that might be able to cancel out immediately. But either way, go ahead, pause the video, try this last question, unpause it when you're done, and see how well you did. Okay, so now that you've had a shot, we have the ability to rewrite as sine and cosine, as we did. What you notice is the fact that I have a tangent, and a tangent in all terms. So I could just get rid of a tangent squared. Turn that into a tangent squared. This would just become a secant squared, and this would become a minus 1. And that would make my life a lot easier. However, to keep in line with what we've been doing, I'm going to go ahead and rewrite all of these as sines and cosines. So sine 4th x over cosine 4th x equals sine squared x over cosine squared x. Secant is going to be 1 over cosine squared x, and this is sine squared x over cosine squared x. The next thing that we notice is the fact that every single one of these has a cosine squared of x in the bottom. I can either get rid of that, or I'll notice that each one of them has a sine squared over cosine squared, and we could factor that out and get rid of it. Either way, it's the same thing as getting rid of that original tangent. So if I factor that out, let's go ahead and cross out what we can. Those both get reduced down to a 1, and this 4 gets reduced down to a 2. So we're left with the sine squared over the cosine squared equals 1 over the cosine squared minus 1. The next thing that I'm going to do is I'm going to try and combine that with the original fraction by multiplying top and bottom by cosine squared. So if I multiply top and bottom, I'll have my bottom, but 1 times cosine squared is cosine squared. I'll notice here that because the bottoms are equal, I can go ahead and multiply both sides by that and just basically get rid of it, which leaves me with the sine squared of x equals 1 minus the cosine squared of x, which can be rewritten through the Pythagorean identity as the sine squared of x. Quadrate, demonstrate them. Done. And there you go.